quiz. And then today is 2 masses. And this could be 2D or 3D, but we'll do 3D. Okay, James, we're starting right in. You ready to go? Good. So to start with, student in the class, Hicks. Who's Hicks? Suggested I show a video, and I like this idea. So anybody has ideas of, there's millions of dynamics videos on the web, and if you see one that you think is appropriate, approximately for some part of the class, send it to me and we can discuss it. So here's one from the news. This was last week or so, and it happens to be apropos. So I don't know if we get sound on this. You don't like the connection? Did we already have the exciting part? It already happened, I think. So what happened is there was a tennis game, and somehow the ball didn't, somebody complained about the way the ball bounced. So watch the way the ball bounces here. And it was in the news, and it was actually, I heard it on the radio, and they had a thing about the science of a tennis ball bouncing. Do you want the lights out, or can you see this fine?
How did that happen?
The question is, how did it happen? So let's say you wanted to know how it happened. You were curious about that, so you went into Google, and you, let's see, what would you want to do if you want to know something like that? You'd ask a scientist, right? Ask a scientist. Not a speller. Scientist. Ask a scientist how a ball bounces. And you ask a scientist and you get, how do balls bounce? Different balls bounce differently. And you get this article on the web, if we're lucky. But I happen to have brought so there's some famous scientist who has something to say about how balls bounce. So I happen to have brought a piece of this tennis court here. And do you want to read this or not? By the way, just to write something like this, just so you know, it takes about, this is probably a full day's work to write these few paragraphs, maybe more than a day's work. And I'm not saying it's the greatest writing in the world, but to write something which is sort of polished takes time. Okay, you can read that for a minute. That's the basic answer to the question about how things bounce. See if it's readable on the internet video. Okay, you can always look it up in Google. You can ask a scientist how a ball bounces and read all about it. Okay, so the thing about 5 seconds more. The thing about collisions is that when they're occurring, all kinds of things happen. So if you take that example up there from the basketball bouncing, we have, in this class, we have this idea of a coefficient of restitution, as if there's some material property that tells you what the ratio is of velocity afterwards from before. But where does that material property come from? It's the property of the basketball, the property of the air, the property of the desk, and the whole mechanics of the situation. And like this essay up here says, it's not just that this basketball is made out of rubber or leather and there's air inside. It depends on how much pressure, it depends on the whole mechanics of it. So if you do like a slow motion video of this thing hitting, you know, it goes down and then compresses, and there's an elastic wave which goes down here, and the elastic wave comes back, and it's so complicated that just this ball, the way it bounces, is different depending on where I bounce it on the table. It's bouncier over here than here. So here's this piece of this tennis court. Somebody asked, is this an official piece of an official tennis court? And I can't lie, it's not. It's a random piece of rubber I found in my lab. But so here's a ball bouncing on a tennis court, and you say, well, that's the property of this rubber in this court. And you look at it and you go, yeah, I guess that's so. And then you bounce it again. Wait a second, didn't do that right. Okay, so it's not a property of these materials. complicated things happen. Now, what's the difference between this? This is a little bit curved, and apparently that's what happened in this tennis court. Is the tennis court itself had a little bit of a blister in it. And so in one case, the ball's bouncing, and then there's some interaction of the ball with the top layer of the court, and a wave goes down, and it interacts with the tar and the gravel underneath, and it's squishing, and it comes back up, and all the elastic energy, or at least a lot of it, comes back. In the other case, the ball hits this thing, which there's a little gap back here. These might even have an elastic collision with each other. It might be that this has about the same mass, or this little region, as this does. This hits, this goes off with some velocity, and it goes off and has a plastic collision down here. Now, when two things have an elastic collision, let's say these two have the same mass. Then their separation speed equals their approach speed. If this one's moving to start with, and their momentum is going to be conserved, this one goes down with the same speed this goes up with. So if these two had an elastic collision with each other, this goes like this, looks dead. And then if this goes down and has some kind of dead or vibrating collision or loses all its energy, nothing happens. So it could be that this goes down with about the same speed, goes down and goos around for a while or bounces some funny way and never bounces back to push this back up. So basically, anyway, the situation with that tennis court is good tennis court, bad tennis court. Okay, Hicks, are you happy?
Yes, very happy. Thank you, Professor.
Okay. Any questions about this example? Or about collisions in general? There's a little cartoon in the book of one-dimensional rods colliding, which is supposed to show you what happens inside. And that's a particular example that people understand. So it's a cartoon in the book of that example. Okay, so you hit a good one. Bonus points, I don't know where they're going to score. God will keep track if you if you make suggestions like that. Okay. 2 lectures ago, we did this problem of a satellite going around the Earth. And we set it up and did it in MATLAB. And when we did that, we had a program or a file that had 3 parts to it. The key important part in terms of concept of this course is the right-hand side file. It's the file that tells you what the differential equations are you're trying to solve. And that's the bottom part when I organized it as 3. And here's the bottom part from the example I did in lecture 2 lectures ago. Then there was a middle part, which was the method, the Euler's method for solving these differential equations. And that's the same no matter what mechanical system you're looking at. In fact, no matter what differential equation you're looking at. And then there was a top part, which was just setting up the problem, putting in the initial conditions, how long we want to integrate for, how accurately we want to integrate, and things like this. So now this is the bottom part for the satellite going around, which I did 2 lectures ago. Okay, now I have a quiz question for you for this. And the quiz question is, in this example, so quiz, how many first order ODEs? And I'll give you some choices. Say again? How many first order ODEs? This is a set of first order ODEs. How many is it? Jennifer Davis here? Who's Jennifer Davis? Hi. Okay. We got you scored now. Okay, good. Good attendance today. One more vote and we'll go. Okay, so lock it up. I'll give you 3 seconds. 1, 2, 3. Lock it up. Should be locked up. Show the votes. I feel like I'm a mastermind of faking you out on these things. I feel like I'm brilliant at this. Okay, so I would say the right answer is not B. So let's go back and well, I'll just tell you the right answer and then we'll score it out. In my opinion, not A, not B, not C, not D, but E, which we got a solid random sample of the class for. Okay. Let's close this out. What do you guys do? Click change your votes quick. I'll get you back. Okay, so what's the how do you read this through? This was a satellite moving in 2 dimensions, and we packed in the state of the system in the number z, which was the state of the satellite. In dynamics, the state is 2 things. It's the positions of all the particles and the velocities of all the particles. Later on, it's going to include the angles of objects and the angular velocities, but those are just different ways of encoding the positions of all the atoms and the velocities of all the atoms, because we'll have rigid objects, and from knowing the angles and angular velocities, we'll know how fast, where everything is and how fast it's moving. So the state of the system is where it is and how fast it's moving. From that, we predict the future, because how fast it's moving tells us where it's going to be. And if we know F equals ma, we know how fast it's moving is going to change. So we know how fast it's moving is going to change. We know how its position is going to change. We go into the future. We calculate it again and again. So that's the basic philosophy. That means we're putting in here the positions and velocities of what? Well, this was a satellite going around a fixed planet. And we can see what we did with that. We pulled out a list of 2 numbers here, which was the first 2 elements of z, and that represented the x and y coordinates of the satellite. And we pulled out the second 2 numbers, which was the x and y components of the velocity. So we had 4 numbers here for z. We calculated a unit vector. This was a list of 2 numbers in MATLAB. We calculated an r dot. This came from v, but v itself was a list of 2 numbers. So here's 2 numbers. We calculated v dot. It had the scalar, scalar, scalar multiplied by ur, but ur was a vector divided by a scalar. Vector in this case is 2 components. So we have 2 numbers here for v dot and 2 numbers here for r dot, corresponding to the fact there were 2 numbers for r and v, and then we packed it up into a column vector, 1 column vector with 2 numbers underneath another column vector of 2 numbers, so it's 4 numbers altogether. So to keep track of a particle in 2 dimensions, we have 4 differential equations. 2 second-order differential equations, which we break into 4 first-order differential equations. Okay, is that clear? Any questions about that? Somebody ask one question, then we'll go on. Yes?
The only reason
Josh?
that the acceleration works in the direction of the vector r is, in this case, because of gravitational acceleration.
Right, so this problem is the right-hand side of the differential equations has to do with the mechanics of the situation. So it has in it the laws of force. In this case, this is exactly Newton's law of gravity. It's Newton's law. This is a force divided by the mass, and that's why there's only, to figure out the acceleration of mass 2, we only have mass 1, because the force on mass 2 is proportional to m2, and the acceleration is inversely proportional to m2, and the m2 dropped out. At any rate, it's a central force inversely proportional to the distance squared, m1, m2, g over r squared, in the direction of the unit vector, but it's an attractive force, and that's the minus sign. Is that clear? Does the highlighting here make it easy for you to read or not? Does anybody have any tips about how to make it easier for you to read MATLAB when I do it on the screen? Do you wish I would do something different in terms of just how I present the MATLAB to make it easier to read? Because, one way to look at this, as I've said before, is you just see a jumble of letters. And I'd like as much as possible that you don't just look at that and say, it just looks like, symbols. No comments? Send me an email if you have a suggestion. Okay, so I'd like to now go on and do a slightly harder example, but only slightly harder. And all of a sudden, we have power to do all kinds of things. And so you'll start, if you caught on so far, all of a sudden you'll realize that you can just do incredibly cool, interesting things. Video blank. Video blank. It just doesn't like to do video blank. How'd that work? Now I lost the whole thing. Okay, whatever it is, I got what I want. Right screen, left screen, raise. Okay, so now let's do the same example again, but rather than thinking about it as a massive planet and a little satellite, and the massive planet just doesn't move, or a planet held by a skyhook, let's do two things that both can move around, and we're out here in outer space, and they're both attracting to each other. So now we're going to keep track of two particles moving around, and the basic setup is exactly the same. So conceptually, there's nothing new. What's hard, I would say, at this point for you is just that it's a little bit of abstraction, that you can just take this powerful idea of F equals ma is a differential equation and apply it to one particle, two particles, three particles, all the same way. So what we're going to do is, let's say, have two planets. So we think of it as a little bit more of a symmetrical problem. And we have some coordinate system over here, x, y, and we can associate it with a I and a j. And we're going to have two planets up here, M1 and M2. And they're going to fly around, and they'll have positions R1 of time and R2 of time. And we can keep track of the position, one relative to the other, of R1, 2. And let's just say we have a gravity attracting these two things, just to do this simple classical problem. This is, the origin of mechanics is sort of based on this problem, so it's a nice one to look at. People were festering about this for hundreds and thousands of years. So how are we going to deal with this thing? Well, we're going to draw free body diagrams. And one free body diagram we could draw is of the system as a whole. And if we draw a free body diagram of the system as a whole, we have this mass 1 and we have this mass 2. And what do we see for the free body diagram? What more do I want to draw on this free body diagram? 1, 2, 3. Come on, with confidence.
0.
Nothing. 0. Right. There it is. 0. No forces. There's no. We're going to. This is out there in space, and we're not worried about other forces from the stars and so on. Then we'd be adding more particles to it. So this is just an isolated system with no forces on it. Right away, that tells us something about how this system is going to move. Because there's no forces on the system, the momentum of the system is therefore constant. Therefore, the center of mass of the system moves at constant velocity. So whatever we set up for initial conditions, there'll be some average velocity of the system, a weighted average or massed weighted average of the velocity, which is there's some point here, which we can think of as the center of mass, and that center of mass is going to move at constant velocity as this thing moves along. We just know that beforehand. Whatever we do, and whatever complicated MATLAB differential equations, any complicated thing we do, it's got to be that the end result is the center of mass moves at a constant speed in a constant direction. Now, that's a consequence of the equations of motion. So when we solve the thing in MATLAB, it's got to be that a property of our MATLAB solution is that that goes like that. Okay, so now we can do the masses separately. Draw the free body diagrams, and we can draw a free body diagram of this one and of this one. And we have a force on this one, and we have a force on this one. And we can call this the force, I'll just call this force 1, 2, how about? And that's the force on body 1 from body 2. There's no standard notation for how to label these forces, but I'll call this F21, which is minus F12. So whatever force acts on this one from this one, the opposite acts the other way. That's the principle of action and reaction, and all constitutive laws for forces have to obey that action and reaction principle. So whatever law we had for the force on body 1, it must be that the force on body 2 is the minus of that. So it's a check of the constitutive law. So what is that force? It's proportional to the two masses. It's proportional to this big distance, to this big G. It's proportional to the R12 squared. And what is R12? It's the magnitude of R12, which is equal to the magnitude of R2 minus R1. And that's that vector which connects from vector 1 to vector 2. Let's see. And that's that distance. And then what direction is it? It's in the direction of U I'll just call this E12. So I'll define E12 to be R12 divided by the magnitude of R12. I very carefully put those went upstairs to get these envelopes and then came down without them. I went up there just for that purpose. Okay, so Pranav's sections didn't get your homework back yesterday. Here they are. So what? Just pass this quickly through this section. I'll pass this through that section, and then when it gets through all the way through, then you switch them around, right? You have to see whether you're in the right section or not. It says the section on the envelope. The other, James, yours got turned back yesterday. Is that correct?
The 4 section, I have the homework section right now on the envelope, so I'd rather not have this floating around.
Okay.
I'm reading that in the class and rather have it outside, so it'll take off.
Okay. So now we've got a free body diagrams of the masses. Any questions about anything over here so far? Yes?
Why in the first free body diagram were there no forces, but there are gravity forces? I don't understand why they're not considered forces.
Why they're not considered forces. So the question is, what goes on a free body diagram? And what goes on a free body diagram is a picture of the system to which you're going to apply the laws of mechanics. And we say the system, in this case, it could be one planet or the other planet or both planets. It could be half a planet, 3/4 of a planet. It could be these two planets and my thumb. It could be whatever you choose it to be, but you know your skill in this class is picking the right thing. In this case, the obvious system is the two planets. That's one thing that goes in the free body diagram. The next thing that goes in the free body diagram is all of the external forces which act on the system. Not all of the forces, but all of the external forces. So on this system, the force between these two things, who has the question? I just want to make eye contact. In this system, the forces between these two things are internal forces, and you don't show them. Okay? Now, if you show them, would it be way wrong? It wouldn't be way wrong because those forces automatically cancel. And it's an assumption about all systems that the internal forces cancel. But it's confusing. So for example, when you draw a free body diagram of a beam in 2020, you don't show all the interatomic forces between the atoms in the beam. You assume they all cancel. And this is analogous to that, it's just bigger. Does that address your question?
Yeah.
Now you could show all those forces and they all cancel, but it's just a confusion, so we call it wrong because it's a useless confusion. Okay, so now we've got free body diagrams, and we can then use linear momentum balance to figure things out. So if we look at linear momentum balance, what do we do with linear momentum balance? Well, we could look at the system, and for the system we have the sum of the forces on the system is equal to the rate of change of the linear momentum. The sum of the forces on the system was 0, and that says that m1 v1 as a vector dot plus m2 v2 as a vector dot is equal to 0. But this quantity here is just vg dot. Because vg dot is d by dt. It's actually the total mass times Vg dot, because if we look at the total mass times d by dt of Vg, and Vg is m1 V1 plus m2 V2 divided by m tot. So here is the velocity of the center of mass. Multiply it by Vg, by the m tot, and you get this expression. The key thing to pay attention to a center of mass is that the total mass times the position of the center of mass is equal to m1 r1 plus m2 r2. Usually you think about the center of mass by putting the division over here, but I find this is actually the equation that you use most often when you're doing calculations, or in this case, the velocity version. What it says is that if you take a sum of all the masses times the positions, it's the same as the total mass times the position of the center of mass. And if you just put a dot on top of all these things, or take the derivative of this with respect to time, it gives you this connection right here. Okay, so what do we find out is that Vg is equal to a constant. And if we want to put this in the world of solving differential equations, it says we know position as a function of time then is going to be, position as a function of time is going to be some initial position, r0, plus some initial velocity times t. So this is actually solving the differential equations. You can think of that as solving the x component and the y component separately, but it's easier to do this geometrically than it is to do it algebraically or in calculus and in components, because what you see is the velocity vector is constant, so it always goes in a fixed direction. It starts at some place, so it goes some distance in the right direction and some time, starting at the right place. But if you're insecure about just doing this step in your head geometrically, break it into components, and you see that you have an x0 and a y0, an x dot 0 and a y dot 0, and you get this result. Okay, so we know the center of mass moves in a straight line. But now, that's the easy part. What we want to find out is how each of these things move separately. So let's just look at, say, mass 1 or mass 2. It doesn't matter which one. So we have for mass 1, the sum of the forces which act on it is equal to the rate of change of linear momentum of that mass. It's always nice to show what equation you're using before you plug it in. On the right-hand side, we have m1 a1. So the forces don't add to 0. They add to that which makes the thing accelerate. It's dynamics, not statics. What are the forces on this thing? There's only one force. If we were doing statics and we only had one force, what would that force have to be? 0. In dynamics, the forces don't have to add to 0. At least if you want the course to be interesting. And what is the force that we have? We have this m1, m2, g divided by r12 squared. There's no vector here, which means I'm talking about the absolute value of it, multiplied by this unit vector, e, in the 1, 2 direction. And that is the equation. Now, we can rearrange this and write this as v1 dot equals, m1 cancels from the two sides, and then we get v1 dot is equal to g m2 over r12 squared e12. If you don't like looking at it in vector form, we could write this in scalar form. In scalar form, it's a little bit of a mess. It says, for example, that x1 dot is equal to, and what's x1 dot equal to? We're taking this equation here, that whole vector equation, we're taking the dot product of both sides with I. That's like taking the x component, and we have to take the x component of this thing. What do we have? Well, we have our gm2, that's easy. And then we have to divide by r12 squared. And what is that r12 squared? It's x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Then we have to multiply this by a unit vector in this direction from 1 to 2, which is x2 minus x1. And then there's an I plus a corresponding j term. We dotted with I, and that's all that's left over, divided by the magnitude of this vector, which is the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. That's what we get for x1 dot. For x2 dot, we get something very similar. What's the difference when we put in x2 dot is that we put a minus sign in front here. Sorry, I wanted to do y1 dot. What's the difference between y1 dot and x? We put a y's here instead of x's, and everything looks the same. And then similarly, we could take that equation in brackets and dot it with j, and we would get that this is a v. I'll get this right. This is a vx1 dot, and this is a vy1 dot. And we can dot with j, and we get very similar things. We get vy1 dot is equal to, and vy2 dot is equal to. And the difference between, too many things to keep track of, x's, y's, 1's, and 2's. In fact, that's an interesting thing. We have x's to keep track of, and v's to keep track of, and y's to keep track of. X's and y's, v's and positions, and 1's and 2's. And those three different sets of two things we have to keep track of. And 2 times 2 times 2 is what? 8. So we have 8 differential equations we're going to have altogether. Okay, so 4 of them have to do with the rates of change of velocities, and then 4 of them are the x dot equals vx, y dot equals vy. That's 2, and that's true for both mass 1 and mass 2. So from this, we get 8 differential equations. Okay, does anybody have any questions about those 8 differential equations? So then we also have x1 dot equals vx1, y1 dot equals vx2, x2 dot equals v. Can't get that straight. vx1, vy1, x2 dot equals vx2, y2 dot equals vy2. Okay, fine. 1, 2, 3, 4, 5, 6, 7, 8 differential equations. You want to stare at it? Tell me what mistakes I made with the 1's and the 2's and the x's and the y's, and ask questions. Yes?
I think if you have on the bottom part vx1 and vy1,
Yes.
each one of those dotted with, well, x v on the bottom, it would be vx1 is dotted with I, and vy1 is when you dot with j. And then in the top part, it should also be vx2 is when you dot with I, and vy2 is when you dot with j.
That's correct. This should be an I. This should be a j. This whole thing has to do with mass 2. And this whole thing has to do with dotting with j. Okay, so now tell me more mistakes. No more mistakes? I'm going to show you an example. And when I went and typed it in, I made exactly these kinds of mistakes about 7 times that I had to fix. How did I find the mistakes? Is I did the simulation, and the masses moved in crazy ways, or I got syntax errors, and bit by bit, I got rid of all the 1's and 2's and x's and y's and v's and x's. Literally, probably 6 or 7 mistakes like that I made in my MATLAB code. And you will too. Okay, any questions about that? Okay, so now what I'd like to do is go back to the computer and show you 2 things. First, I want to go back to the single satellite problem and just show you a little more fancy stuff that we can do with that single satellite problem. And then I want to use that fancy stuff to do this 2-planet problem. So if you don't understand what's here, it's sort of going to be useless. So maybe just take a couple questions here before I go on. Stupid questions. Ask really bad questions. Yes?
I mean, in MATLAB, you don't have to enter all of the scalar forms, right? You just use the
Right. So just like I showed you up there, and that was the point of the quiz question, was to make you alert to that. If you have this nice vector form, you don't have to break it into scalar form. You can let MATLAB keep track of that. So I didn't have any mess like this when I did that single satellite problem, because I left these two components together. I calculated this magnitude as a number. I just asked MATLAB for the magnitude of the vector, and I never had to write this formula down here. So you don't have to write this. Your code doesn't have to show this mess if you use MATLAB correctly. Does that address your question? Yes?
Doesn't the vector change direction?
Does the vector change direction? There's lots of vectors here, and they all change direction in time.
Keep track of that in MATLAB.
And that's the whole idea of solving differential equations in MATLAB, is keeping track of how things change in time. The main things we're keeping track of are vectors. And the main vectors we're paying attention to are positions and velocities. And the whole thing of solving the differential equations is keeping track of how the positions and velocity vectors are changing in time. That's the whole project.
Wait, but so you're saying you don't break it down into components, you just keep that one equation in MATLAB.
This one equation is 2 of the 8 equations. There's another one for the velocity of particle 2. That's 2 more. And then there's 2 more each for the relationship between position and velocity. So we'll have 4 two-component vector equations, which will assemble into a list of 8 equations.
I'm saying, how do you write a vector equation?
That's what I just did in the previous example, and I'll show it to you again if you like. That's what I was trying to show you in the quiz question. Remember, we counted, it looked like 2 equations. A lot of people said 2 equations, and the right answer is 4. That's because R represented 2 numbers, an x and a y component, and V represented 2 numbers, x and y components. Does that address your question? Okay. More questions? Yes?
How would you solve the vector differential equation on MATLAB?
Exactly. Precisely my point. I'll get to that in a minute. Next question. That's what the course is about. That's what the lecture is. Today's the topic of today's lecture. Next question. Okay. So next thing is, can I make this thing work? Send to center display. Video blank. Not video blank. Laptop. Send to center display. Aha. Center screen. Down. Okay, let's talk about room lighting. Room lighting. I think when the room is dark, this projector might be too bright. Or would you like the room a little dark? Who would like the room a little darker? Raise your hand. A little darker. So I want to get the house lights front down, if I can. Podium lights. Too dark. Too light. We're getting there. Oh! Good? Best? Optimal or too dark? Good? So those of you who get headaches, bring sunglasses. Okay, so now we're back to the one satellite problem. And here is the differential equation for one satellite. We've got this gunk of code up here, which is just coding stuff. For example, in the differential equation, we have parameters like the 2 masses. And this is just the one this is not the new problem. This is the last problem still. and we coded them up inside this structure called P, and to make it easier to read below, we pull out P.M1 and called M1 and so on. So this is just a junk line setting up parameters. Then, in solving differential equations, we just think of it as being a long list of numbers from which we predict the rate of the long list of numbers. So comes in a long list of numbers, and comes out the rate of change of that long list of numbers. But we think of those numbers as having meaning, so the next part of the code is just unpacking those numbers to give them meaning. For example, the first two numbers are the position, x and y components. So here's how we have two numbers hidden in one vector in MATLAB. And the second two numbers are the velocities of that mass. And in this case, it's just one mass, because I'm not doing the new problem. I'm doing the single satellite going around the fixed planet. And in this case, I wanted to know the length of this position vector. And there are different ways of getting this in MATLAB. You could take r1 squared plus r2 squared, the square root. You can take the dot product and the square root. Or there's actually a MATLAB command called norm. I could have just typed in here norm of r, and it would give the same result. Okay, there's different ways. It's so common you want to know the magnitude of vector. There are lots of ways to calculate it. And then, so this is now just a scalar, and then we calculate a unit vector, ur, which is r divided by the magnitude of r. So this is all just set up. Get it out of your heads. Any questions about the setup? Now you say, how do we get 4 differential equations without having to write all that stuff with the square root of x minus x squared plus y squared and all that stuff? As we said, well, first of all, if we know the velocity vector, that tells us the rate of change of the position vector. Now you can read this as the first element of the velocity, vx, is the rate of change of x dot, and the second number, vy, is the rate of change of y dot. But this is a lot tidier, and it gives you a geometric picture also. The rate of change of the position vector is the velocity vector. Then here is the laws of mechanics. It says the rate of change of velocity, otherwise known as the acceleration, is given by Newton's law of gravitational attraction, G m1, m2. How come there's no m2? It's because there was an m2 on both sides of the equation and it crossed off. The gravity force is proportional to the mass, but the acceleration is inversely proportional to the mass. And then we have divided by the distance squared multiplied by unit vector in the right direction. And this is 2 equations. It's got 2 components for the rate of change Vx and Vy. And over here, this unit vector is giving the direction of the force, has 2 components. Then we pack this up into a list of 4 numbers, the first 2 numbers and the second 2 numbers. Okay, that's how you take a vector equation and write it as 4 scalar equations. Does that address that question that you asked? I don't know your name, the guy who asks all the questions all the time, who's not paying any attention. Does that address your question?
Yeah.
What's your name?
Legion.
What is it?
What?
Leja?
Legia.
Leja, okay. Does that address your question?
Yes.
Okay. Now what I've done here, differently than I did last time, and this is now about MATLAB, not about mechanics, is I put this in a separate file. So this is up here in some file called satellite right-hand side. So previously when I showed you this example, I put 3 different blocks of code in one file. Now I have it in 3 different files, and I'm going to show you those 3 different files. The right-hand side file, the differential equation file, and that here is our Euler integration, and this solves all differential equations. So you take and you say, whatever the differential equation is, I'm going to solve it. It's got to be in this program called right-hand side. How am I going to solve it? Is I'll decide on how many points there are. I'll look at the parameters. I'll pass the parameters through. I'll use the initial conditions, and I'll solve it. So I set up this messy thing, which is a list of times. These are times I'm going to step forward. I'll set up just calculate the step size. All this is taking the length of the time interval and dividing it by the number of steps, or taking the difference between the first 2 times. I set up an array which I'm going to store my solution in. Each row of this array is going to be the list of x's and y's and v's at each time. And then I have my solution to the differential equation, which works for all of mechanics and all of science. So this is all of math 2930 in these 3 lines of code. We can solve every differential equation. Okay, now what are these lines of code? It says, let's look at what the state of the system was at the last time. So this is one row of the solution matrix. but we're going to write it as a column, and that's just a MATLAB thing, which we don't have to do, except for we have to do it when we start using more fancy MATLAB programs. We have this array of times, which is just a long list of the times of the solutions. And then how do we go into the future? We say the new value of all the variables is the old value plus the time step times the rate of change. What's the rate of change? It's the thing that we calculated in this right-hand side program. In the satellite right-hand side. Where was the satellite right-hand side program? So now, let me just show you the fancy syntax thing that happened here, is that in calling this thing, we use the top part of the program where we set this up. We say clear everything, let's start at a certain time so we can tell what's happening with debugging, let's define our parameters, let's say how long we're going to solve the problem, let's use how many steps we're going to use to solve it, let me not do so many steps so I don't waste time, let me put in the initial position, the initial velocity, a list of 4 numbers of position and velocities, and now I'm going to ask my little Euler solver, which solves every problem, to solve this problem. So I give it the initial time, I give it the initial conditions, I tell it how accurately to solve it, I tell it what the parameters are, and I have to tell it what the differential equation is. So the fancy thing I did is I've now called a program, the one I wrote, the one I just showed you, a little function, and said solve a differential equation. I said which differential equation, and rather than call all the differential equations the same thing, I've given this a name. So I have a differential equation called satellite right-hand side, which is this one. And Euler method needs to call that, but Euler method is a general purpose solver, so it's always going to solve right-hand side, but now right-hand side is going to represent a text string. So the tricky line in syntax here is this one here, and so if you want to write this down, something to look up, it's Feval. So this is the fancy new command I've used, is Feval. So let me just quickly show you what that command is. If I go sine of pi, what's the answer of sine of pi? What's that? What number is that? 0. Right, e minus 16, that's 0. Now if I go Feval, and I put a quote, and I put sine, and I put pi, it gives the same answer. So what the Feval does is the first argument is a text string. It evaluates that text string with the argument, which is the second one, or the list of arguments. Now, why would you want to do that? Is because, for example, over here, everything's going to go crazy on me now. Over here, we have our satellite right-hand side. We want to call that from our Euler method. But we might want to solve different problems with Euler methods, so we say whatever problem we're going to solve, it's going to be in this text string right-hand side. So we set up the problem, we say the problem we want to solve, the differential equations are in this thing called satellite right-hand side. We pass in the text string satellite right-hand side when we call the program. So back over here in the program satellite 2, we pass this text string in. That gets passed in to the Euler method in this variable right-hand side. It now has the character string value, satellite right-hand side. So when it calls Feval this, it calls the right-hand side function, the one we want, which is this satellite right-hand side function. Okay, and I will post this on the web. Okay, so now I've broken these 3 parts into 3 separate files to make them conceptually more clear. Any questions about this? And I put them all into a separate folder so that it's Now class is over, is that what happened? And I'm only halfway through. I guess I have no choice. We will pick this up before the prelim. Just 1 minute, just for your benefit. Does anybody have any quick questions about the prelim? Yes? Does anybody want a question and answer review on Saturday? The only offer is Saturday. Okay, well, Saturday afternoon we'll have some question and answer session someplace.